So the key point we're still talking about the rate of reaction, factors that affect rate of substitution. Okay. Factors that affect the rate of substitution. So we talked about the basicity, we talked about, I think, size and shape, and now we are talking about polarizability. So polarizability can be explained in so many different ways. We still have to consider the solvent effect that will affect the polarizability of the nucleophile. So this is part C, and it should be slide 14, starting from slide 14. So what I want you to know about polarizability is, before considering the solvent, let's keep in mind two things. Think about the size to start with of the nucleophile, and next we're gonna think about the solvent type. And there are two types of solvent. I talked about it: a protic, that should be a P, and protic. So now to really explain what happens here with the nucleophile, remember the nucleophile is the guy that does the attacking. The nucleophile must have a lone pair to attack, should have a negative charge, at least, like iodine. Okay, iodine is a nucleophile. It's bigger than bromine. You go down the group 7 elements in your periodic table. And bromine is bigger than chlorine or chloride. And then chloride is bigger than F-. Now, this is going to be the biggest. And you are using just group 7 as an example. The same concept applies. The same concept applies for other groups that could make anions. Metals don't make anions, they make cations. So we don't consider metals, we consider non-metals with this. So I'm going to give you a shortcut here. So in terms of nucleophilicity, okay, which means the ability of the anion to be a nucleophile, in terms of nucleophilicity, I-, which is biggest in size, will be the best nucleophile in protic solvents. I'm really giving you the summary of the whole thing. F- will be, so I said I- will be the best nucleophile. Let me say, put it somewhere here. Let me write it here. Best nucleophile in protic solvents. That's the key statement that I have to, because you're going to be asked to rank which of these is the best nucleophile in this solvent. So you have to know what a protic solvent is. Consider size. We are talking about nucleophilicity. Under nucleophilicity, we are talking about polarizability. Okay, so now F- will be the best nucleophile in aprotic solvents. Can someone give me an example of protic solvent?
Acetic acid.
Okay, and why do you think acetic acid is protic?
Because it has the carboxylic acid on it. It has the hydrogen attached to the electronegative oxygen.
Correct. Protic solvents are solvents which have hydrogens bonded to oxygen, nitrogen, or fluorine. So which means water is protic, methanol, any alcohol is protic, including the one that you guys drink over the weekend to forget your troubles. Ethanol is protic, which means also methylamine is protic because those hydrogens are bonded to nitrogen. HF is protic if it's in liquid form. That's protic. So those are examples of protic solvents. Someone give me the examples of aprotic solvents.
Acetone.
Yes, nail polish remover. And I will draw these hydrogens. You'll see those hydrogens are bonded on carbon. Carbon is not one of these guys. It's not very electronegative. It's not, super electronegative. So this is aprotic. Switch the carbon with the sulfur, you get what we call dimethyl sulfoxide. And very soon in the future lectures, we'll talk about dimethyl sulfoxide, DMSO as a solvent. This is acetone. You want these guys usually for SN2. The other one is acetonitrile. SN2 prefers aprotic solvents. How do we draw acetonitrile? Okay, I think that should be acetonitrile. So I've given you the idea here. So now let's try and answer some questions. Okay, before that, let me explain what polarizability means. So assume you have an electrophile, a common electrophile. Okay, I'm gonna slide this. So assume you have a common electrophile and you have iodide reacting with a common electrophile. So let's take this to be our electrophile. This will play the role of a nucleophile. It does the attacking. This plays the role of an electrophile. It's gonna be attacked. So SN2, you do attack from the back side. You attack the carbon that bears the leaving group. We call that carbon alpha because it's bearing the leaving group. And it's going to be partially positive because of dipole moments, right? So you expect this bond to break towards the chlorine because chlorine is more electronegative. So to show your product, you get I there, and then you're going to get Cl minus. Now, I said this is going to be the best nucleophile if you have solvents, let's say like water or any other protic solvent. Iodide will win. Like the rate of reaction is going to be faster. What is the reason? The reason lies in the microscopic state of what's happening, what we cannot see with our human eyes. The water molecule has dipole moments, so hydrogen will be partially positive, oxygen partially negative, or because oxygen is more electron withdrawing, it's electronegative. So if you bring your iodide, one would consider size, and one would say iodide is big, hydrogen is small. If you try to hug a sumo fighter, you being the hydrogen, the sumo fighter being the big guy, being the I minus, there's going to be very less of a grip. Like you're not going to be tightly bound to that guy. So the intermolecular forces between I minus and hydrogen is weak. So we call it weak IMF, weak intermolecular forces. So which means the I minus is very much available. So I minus is very much available to do the attack like it's doing up here. It's not trapped or bound to the solvent molecules. Compare that to F minus, the baby-sized F minus. If you do this, again, with the same protic solvent like water or methanol or acetic acid, the reaction will go, but not quite as fast. The reason is the water molecules have the hydrogens that are partially positive, and those hydrogens are equally sized to the F minus. So in this case, there's going to be a very strong intermolecular force of attraction. The name is what? Someone tell me, what's the intermolecular force of attraction between H and F?
Hydrogen bonding.
Hydrogen bonding. We discussed hydrogen bonding in earlier chapters. We said hydrogen bonds are very strong. So which means the solvent traps the nucleophile. So this guy is not very much available to attack that carbon because it's already trapped by the solvent molecules, which are more. You know, a solvent is something that dissolves another thing. So you expect to have so many solvent molecules. In this case, they are protic. They mask and trap the F minus. And the F minus is not available to attack the electrophile. So the rate of reaction here is going to be very slow. That's the understanding on how these things work. Now let's come back to polarizability, because once you understand this, it's easier for me to explain to you what polarizability definitely means. It has something to do with this, but using orbitals, I want to explain that. And that's what's shown on slide. Where is it? Which slide number is that? That's what's shown on slide 12, I think. So assume your big iodide is coming. Okay, it's big in size, so it wants to attack your positively charged, partially positive charged electrophile. So this guy will bear a partial positive charge. So there's gonna be a partial empty p orbital right here. So you know, because of the structure of the electrophile, this iodide should not just straight ahead go there and attack. It does not happen like that. It changes in shape so that it fits this pocket. We call it a pocket. So for the I minus, big I minus to fit in here, it's gonna change in shape. So instead of taking that shape, it's gonna kind of flatten out a little bit. That's the only way it's gonna come in here, okay, and do an overlap with the other orbital, which is this guy, to make a bond. Okay, so that's what it does. So this kind of change, conformation change, is what's called polarization, because now your electrons that are in iodine will kind of move on one side. So they are polarized. So that's what we call polarizability. And polarizability is only possible if the anion has a big shape or a big size. So if you do that with fluorine, fluorine is already small. Fluorine is already small, and it kind of going to have a hard time flattening, giving it a more big flattened shape to have the electrons like that. In fact, there is just less volume of electrons to be on that side of the F minus. As the F minus tries to come and attack the partially empty p orbital, what we call partial positive charge. So you see, there's not much conformational change for F minus. Sorry, this should be F minus, as compared to I minus. So the big size helps the iodide to change its shape. And doing so, the electrons are kind of pushed on one side. That's what we call polarization. And now those electrons, electron density there, will be used to attack the partially positive center of the electrophile as the chloride leaves. So that's the idea. And I've really tried to explain it. There's no other way
and
to...
This is in an aprotic solvent, or
no, right now I'm not considering the solvent. Notice I've not mentioned any.
Okay.
I've not mentioned any solvent here. There's no, because now if there is protic solvent, then this guy doesn't even have a chance. It's gonna be trapped with the solvent by hydrogen bonding, right? So, and if you consider the opposite way, if you put this iodide in a protic solvent, it's not gonna be helped to work. So I'm not talking about the solvent here. Here I'm just considering the shape and size. Okay, so in terms of polarizability, I minus is well polarized compared to Br minus, compared to Cl minus, compared to F minus. So without thinking about the solvent and just basing on polarizability, I minus should win, because it changes its shape more readily as it attacks the electrophile. So now I've given you two scenarios. I would want us to do some questions here. Rank the following nucleophiles. In order from the strongest to the weakest when used to do SN2 reaction in isopropanol. Isopropanol. I wrote the pro twice, so it should be just isopropanol. So let's say you have a nucleophile. Generally, a general nucleophile, you want to use it to do this SN2 reaction. What should I use here? Let's see, what should I use? Okay, let me just use that. This inversion of configuration, that because I'm assuming it's SN2. This is isopropanol. You might ask yourself, what's isopropanol? That's isopropanol. So nucleophiles, you have the nucleophiles you're given is, you're given Br minus, you're given I minus, and you're given F minus. So who is the best nucleophile?
I minus?
Yes, it's gonna be I minus because I see the solvent here is protic solvent. I don't want to say a protic solvent because that will confuse it. The solvent is protic. So I minus will win, and then Br minus, and then F minus. So what if you're asked to do the same thing, and this time the solvent is, so let's do the same thing, but this time the solvent is DMSO. So you have your nucleophile, you have the leaving group there, but now this time your solvent is DMSO. You're thinking SN2. Who wins?
F minus.
Correct. Because this DMSO is a protic. I drew the structure for DMSO before. That's the structure for DMSO. Those are methyl groups. CH3, CH3. Those are methyl groups. So it's a protic. In a protic solvent, F will win. In protic solvent, I minus will win. So the ranking will be F minus is a better nucleophile than Br minus, which will be better nucleophile than I minus. Okay, so remember here F minus on the top question. This one is losing because it's gonna be trapped by the solvent. It forms hydrogen bonding. That's the problem. Okay, we have isopropanol, so probably I should draw the isopropanol structure. So I used water as an example in the previous slide, but here we have isopropanol. Still, isopropanol is protic, so the hydrogen gets trapped. The F minus gets trapped by the solvent molecule. It's not going to be used to do the reaction, so it's the least reactive. If you have a question, ask before I do the next concept. No question. Okay, so let's talk about effect of leaving group. Effect of leaving group on SN2. So now I'm gonna take you back on earlier chapters. I think you're tested on this in exam 1. The key point you want to know about the best leaving group is the best leaving group must form, this guy must form weak base, weak conjugate base, I would say. Must form weak conjugate base after leaving. Like, I can't emphasize this enough. But you guys know what makes a weak conjugate base. What makes a weak base? Let's just say what makes a weak base. It's gonna be stabilization by 1. I think we said resonance. And I'm going to give you an overview for this. For example, if you have OCH3, let me see, OCH2, CH3, so let's say there's a negative there, versus O minus. So which one is a weak base? Is it gonna be A or B? Based on resonance.
B.
Correct. Because you can push this one this way and that opens up. So this guy is the weakest base. So the next factor you look at is electronegativity. So compare OH minus and Cl minus. Who is the most electronegative? Cl minus, OH minus. Someone, anyone?
Cl minus.
Correct. That's the weakest base. So which means the ones I'm circling are the better leaving groups out of the pair. The next one is size. Remember, whenever you're looking at size, that is only considered if elements are on the same column. Elements on same column. So in this case, I minus versus F minus. I minus is big, so this will be the weakest base. And if it's the weakest base, it's the best leaving group. Okay. So those are the things that you consider, the 3 main things you consider for leaving groups: stabilization by resonance, electronegativity, size. So now let's go to examples as usual, which is why I'm here. So let's say which let me find an eraser. I'm sorry, I've been talking my language since morning, so my brain is slowly trying to come back to English. Which of the following, are you laughing at me? Which of the following will react fastest in substitution? And I'm saying substitution because it's going to apply for both SN1 and SN2. We'll talk about SN1 next week in substitution reactions. So it could be SN2 or SN1. We've not discussed SN1 yet, but don't worry, we'll talk about that. So A, I'm going to draw 2 molecules. You tell me who will react fastest. That one has an I, and this one right here has a BR. Tell me the answer.
The one with the I.
Yep. all because of size. Once I leaves, it gives you I minus. This gives you I minus. This gives you Br minus. I minus has more space for electrons to stay and reside. So it's a weaker base, which means it's a good leaving group. Okay, the next one is OH versus NH2. Who would react fastest, if possible? I know this one is unrealistic, but just use the idea to tell me the answer. Somebody tell me the answer.
NH?
No. You know, nitrogen is less electronegative than oxygen. So assume the OH went off. You know, we are considering leaving groups. So if OH falls off, you're gonna get OH minus. If NH2 falls off, you get NH2 minus. The element bearing the negative charge is the oxygen in this case, and is the nitrogen in that case. Electronegativity increases across the periodic table. CNOF. So oxygen is more electronegative than nitrogen. So oxygen holds on the electrons tighter than the nitrogen, which means OH minus is a weaker base than NH2 minus. Both of them are strong bases, but comparatively, OH minus is a weaker base than NH2 minus. So NH2 minus is going to be a stronger base. So it's going to be a poorer leaving group compared to OH minus. So in this case, this would react faster. Okay, so the factor I used on the first one was size. Let's take notes. I used size to answer that. Here I'm using electronegativity of the element bearing the lone pair. Trying to shorthand here. Electronegativity helped me there. Okay, now let's do the next one. Here you have a common element. Who will win, structure A or structure B?
A.
A will win, and I think I'm assuming the reasoning is you telling yourself this whole thing will fall off. You're not cutting here, you're cutting on this bond. If the nucleophile attacks from the back, it's that bond that will break. So you're gonna get O minus. That will be your conjugate base or leaving group. That's your leaving group. In this case, this is the bond that would have been broken if this were to be possible. In this case, you get OH minus. So definitely, you see, you have the same type of element carrying the negative charge. It's the oxygen in both. So here you cannot use size because it's the same thing, OO. You cannot use electronegativity. It's the same thing, OO, equally electronegative. So the factor we're going to use here is, someone tell me?
Resonance.
Resonance. So the conjugate base from structure A is resonance stabilized, which means those electrons are hidden within the structure. They are not available for this guy to play the role of a base. You know, bases must have electrons available on the structure to be used, but here the electrons keep on dancing around. You can't tell where they are. They are not easily used. So this structure here, the carboxylate, we call it an ethoxide. Ethanoate is a weaker base than the hydroxyl group, the hydroxide. So I would expect this structure A to be the most reactive because it has the best leaving group based on resonance stabilization, which makes this leaving group a weaker base compared to OH minus. If you have a question on those examples, let me know before I move to solvent effect. Perfect. Okay, so next point, which is point number 3 on slide 18. So we are looking at effect of solvents on substitution reactions. Okay, so I said there are two types of solvents. We have protic solvents and we have aprotic solvents. So if you are sleeping when I was talking, protic solvents have hydrogens bound to oxygen, nitrogen, or F. A perfect example would be H2O here. A perfect example would be acetone here, because acetone does not have any hydrogens bonded on oxygen, nitrogen, or fluorine in the structure. So now, the clue I'm going to give you right now is this, because you're going to be tested in exam 3. Protic solvents favor, I don't know if you have a U in American English or that's British in me. These ones, protic solvents favor SN1. They disfavor SN2. It's going to be the opposite for a protic. Aprotic solvents favor SN2. They kind of disfavor, I say kind of because there are other factors we look at, kind of disfavor SN1. Okay, that's what you have on slide 18, but I'm gonna explain why, because we are talking about SN2, I'm gonna kind of explain SN2 here and the effect of the protic solvents, what they do. So assume, in SN2 case, assume you have this reaction. So assume you have a nucleophile. I know in the notes you have metal sulfide. I'm not going to use the same one because I recorded that video. I'm going to use a different example. So assume you have OH minus as your nucleophile, and it could be any negatively charged nucleophile like what's in your notes on slide 19, sorry. If this nucleophile is in the presence of water, probably it wants to attack this to get alcohol and Cl minus. So if the solvent here is water, then there's going to be a problem, because I told you the nucleophile will kind of most likely going to have hydrogen bonding, because this is partially positive. You know the oxygen is negative, so you get strong hydrogen bonding. So in that case, the nucleophile is trapped by the solvent. But I started by telling you last class, I told you that for SN2 to go, you really need a strong nucleophile. And not only should it be a strong nucleophile, you want it to be available. Here the nucleophile is trapped by the solvent. So the nucleophile is not available. So this reaction most likely is going to fail. Or if it happens, you're going to get a very low yield. So you don't want that. So to avoid this, we use acetone and such kind. So in this case, I would prefer to use acetone, because now if you're using acetone for the same reaction, look at what happens here. So you have the hydrogens right there. I'm just going to show the hydrogens next to the OH. Those hydrogens are not very super positive, because these hydrogens are not bound to oxygen, right? So you don't expect, there's going to be no H bonding Why? You don't have protic solvent. This solvent is a protic. In this case, we had the hydrogen bonded to oxygen. That's why it was super partially positive. But here, this hydrogen is not as positive. So there's no hydrogen bonding. So which means the nucleophile, which is OH minus, is very much available. If the nucleophile is very much available, if I switch the solvent here to acetone, there's no brainer. This reaction will instantly happen. The nucleophile, the strong nucleophile is available. It's not trapped by the protic solvent because you are using a protic. The reaction is likely to go at a quicker rate. So that's what happens with the solvent. That's the role of the solvent. The solvent will either help the reaction to go or compete with the reaction and hinder the reaction from going. Do you have a question on that explanation? You could ask. No question. So I'm still going to emphasize it one more time. One more time. I'm going to emphasize. If you have OH minus reacting with an electrophile, your solvent is a protic, which is what you want. The reaction is likely to go quicker. There are two things this solvent will do. Let's say the nucleophile came in as sodium hydroxide, right? Sodium hydroxide can be written as such. We don't care about the Na+. We just care about the nucleophile. So the solvent, one thing the solvent will do is to take away the Na+, because the Na+ is going to be joined onto the lone pair of the carbonyl of acetone, okay? The solvent. So which means you're going to be left with OH minus by itself. In this case, we usually say the solvent helps to make the nucleophile naked. It's made naked, in other words, no longer bound to Na+. Okay, the nucleophile in this case is OH minus. So you know your reagent is sodium hydroxide. So the Na+ is taken out in this manner. It gets bound to the solvent molecule. You want it not to be bound to OH because you want the OH to be by itself. So that's one role of the solvent. The other role of the solvent is you don't want it to be trapped. You don't want it to trap the nucleophile. See, in between here, there's no H bonding. Again, to repeat, in the other case, in red, if the solvent was water, too bad. The water is gonna trap the nucleophile because now the OH minus is just gonna get trapped to the partially positive hydrogen because this solvent is protic. You have the hydrogen bound to oxygen. So in this case, you have strong H bonding. So if you did not get the explanation the first time, this time it should be clear. So that's the role of the solvent. But now in SN1, I'll describe why you want protic solvent. It stabilizes the carbocation. We want that. So SN1 is favored by protic solvent. SN2 does not want protic. Here it's SN2 because it's one step bimolecular, no carbocation intermediate. This one does not want to happen because of this protic solvent. Here, anytime SN2 will happen because there's no competition of the solvent with the nucleophile. In fact, the solvent is doing just the opposite. It's helping the nucleophile to stay by itself as a standalone, so it does its job by taking away the counter ion, which is bound onto the structure of the solvent molecule. Okay, so now lastly, before we do that, let me ask you, which of the following which of the following is the best solvent for an SN2 reaction, which is a typical question again in the next test. So A, you have hexanol, B, you have water, C, you have ammonium hydroxide, and then D, you have acetone. Answer? It's gonna be D, right? Because out of all these, this is a protic. For those who are wondering what's ammonium hydroxide, it's NH4 plus OH. You have an OH there. Water obviously has an OH. Hexanol, 6 carbons, 1, 2, 3, 4, 5, 6. That's an alcohol. 1, 2, 3, 4, 5, 6. Still, there's a problem there. All these guys are protic. These guys are protic. You want a protic. You don't want the solvent to compete for the nucleophile. Okay, let's see. I think we have the last one, which is the easiest to explain. Yay! Okay, screen, let's see.
Yay!
Yeah. Yeah. Let's see if I can. It's not letting me bring a scan. Let's see. Give me a. Okay. Will you let me write? Thank you. So the last factor is the structure of electrophile. Effect of structure of electrophile on SN2 reaction. We've talked about nucleophiles all this time. Now, what about the electrophile? So assume SN2. Assume SN2. Let's see. Assume SN2. Remember, all these guys are nucleophiles. All these guys going down are electrophiles. Assume SN2. Who do you think, which electrophile do you think has much access on the backside? Because remember 2 points. We said SN2 proceeds by back attack, right? That's how you get inversion. There's back attack by nucleophile. And you're assuming that you are going SN2. The nucleophile is the same in all these examples. So which of these electrophiles do you think has space, the most space on the backside to be attacked? Is it going to be A, B, C, D?
D.
D.
Methyl bromide?
Correct. The moment you add alkyl groups, those alkyl groups are causing what we call sterics. So this guy here, the tert-butyl bromide, is the one that's going to be so much sterically hindered on the back. So this nucleophile, as it bounces and comes in here to try to attack, one of these metals will be throwing it back. It tries to come in, it throws it back, because these metals keep on rotating like you rotate your hand. So you have too much sterics here. So the more R groups meaning alkyl groups or carbon-containing structures, the more R groups you have on the back side of the electrophile, the more steric hindrance or crowding you have on the back, and the slower the reaction will go. So this guy will go the fastest. just because the backside you only have the baby hydrogens. If I was to draw the 3 hydrogens, those are the 3 hydrogens you will have on the backside. They're not big, so you have much space on the backside. So you'll attack the carbon and then the Br falls off. Definitely the product will be that plus Br. Here you will do the same thing, but the reaction will be slower than D. One would expect the product to be that plus Br. All these are assumed SN2s. If this happens, because that's a secondary carbon, then you're gonna get that plus Br. Here I would expect no reaction. So in summary, SN2, which is the key point if you are taking notes, and you should write this down. These 2 points I've written up here, they are very important for this part. Step number 4 in your notes. So SN2 works faster with metal halide. So X could be Br, could be Cl or iodide, never F, never fluorine. So this is metal halide. It's going to be faster than a primary alkyl halide. Primary alkyl halide will do a fast reaction compared to secondary, and secondary will be faster than tertiary. Never, this is another point, never do substitution on sp2 carbon. So for example, if I had OH minus plus this, that's an sp2 carbon. The answer is no reaction. If it's SN1 or SN2, this will fail because this carbon right there is sp2. Never do that. These carbons that we've been using here are sp3s. So that's fine. We would give them a chance to work. But for sp2, never do that. So here I would add sp2 carbon. Okay, so rate of SN2 again.
Why do
Yes?
carbons not?
Yes?
Why don't sp2 carbons react?
Because they have a higher S character. You know, in sp3, that's the only explanation I can give, the simplest explanation. In sp3, the S character is 25%. In sp2, is 33.333%. In fact, I should add here sp2 and sp. Never do substitution on sp2 and sp. Only do substitution on sp3. sp2 has 33%. sp has 50% S character. So you never do substitution there, because again you have less of a p orbital in there. Yeah, you have less p character as you go down, sp3, sp2, sp, and you are throwing electrons in the p orbitals. That's the technical explanation. But just know, never do substitution on sp2, never do substitution on sp carbons. Those ones have less p character compared to sp3. That's why. So again, rate of reaction for SN2 is the opposite of SN1, E2, and E1. It's always metal X will be more reactive than primary alkyl halide. Primary will be more reactive than secondary, secondary more reactive than tertiary. And then, of course, you don't want to do substitution on sp2 on sp2 or sp carbons. Never do that. And that concludes today's class. I'm not gonna send you pre-quiz because I know you're studying for your Thursday. I'm not gonna send you, post-class, but I'll send you pre-quiz after the test. So which means on Friday or after Thursday test. All right, have a nice day.